All right, how we doing today, all? Good. So, how do we feel after last Thursday? How did workshop go? Did it go? We have no thoughts. What's that? Yeah? How many attempted Romance JS this weekend? Cool. Okay, and then show of hands, how many of us think we're in a good spot with the course so far? Okay, okay. All right, so just as a recap, high order functions, the stuff that we're going to do today is not so important to be able to get into the boot camp. A lot of the stuff in functional programming in general can really clean up a code base and make things a lot more maintainable, and it can make your life a lot easier. But we could still do things the old, less fancy way if that's what's easier for you. I would still recommend ultimately adopting this style. But if you don't fully grasp what we do today, which is going to be a little bit tougher than last week, that's okay. So some of the stuff we're going to go over today, my coworkers don't even know how to do, and I'll show you where it's really useful and how it's made problems in our code base because they won't write in this style. That being said, today is definitely a lot more skill-based, whereas last Thursday, you still don't need to know it to get into the boot camp, but being able to use the basics of higher order functions like for each, map, and reduce definitely make your life way easier to solve problems because there's a lot less to debug when we're just doing a for each and a map versus you manually creating the for loop yourself, having to worry about the indexes, plucking out the variables, and just putting a lot more code on the screen that you could have problems or you have to translate. And in general, that's going to make bigger problems that have a bunch of for loops a lot more wordy than if we did it the functional way. So I still recommend that definitely when we go to practice after this course, you want to get good with the stuff last week because it's just going to make your life so much better and make you, when you understand it, you'll have a much better grasp of how to approach problems. And today we don't have to worry about as much, but it's still really important. So get as much out of it as you can, or at the least be aware of it to come back to and start making functions that generate functions so you could just reduce patterns in your code base that appear over and over again. If we can isolate them to functions that can just generate a recipe that does the same amount of work with any parameters, again, there's a lot less code, and that's where you can really demonstrate a skill gap above the people you go to boot camp with, the people you compete with for jobs, and then even when you get the job, the people that are on your team. And this is definitely a skill-based career, so the more you put into it and the more you can demonstrate your thought processes behind code and how it helps a code base, well, you get to command a higher salary and you get to be pickier with which places you want to work for. So it's definitely, don't discount it entirely. I'm only giving you a disclaimer that's not so important, so you don't beat yourselves up if you don't get it immediately. All right, so before we get started, do we have any questions? Yes.
This is being recorded, right?
This is being recorded. I did record Thursday. I just got distracted, so I have to upload that right after lecture, but we do have the video. And so this is already being recorded, so just skip through these first 10 minutes.
Perfect. That's good.
Cool. All right, let's get to it. So I just want to do a little bit of a review. What method did we learn that basically eliminates the need to manually set up a for loop in 99.9% of cases? For each. So I've got this list of numbers up here, and basically for each number, I just want to log them out. What can I do? So let's think about the problem I just said. What is the real logic that we want to do for each number? What is it? Yeah, so what can we, that pattern, that work that we want to do, what can we set up here? So before we get to that, before even thinking higher order functions, at its base, I want to take in a number and I want to log the number out, right? So that's the level we're thinking at right now. What can I do? And just for the sake of making this easier to grasp at first, I'm not going to make it an anonymous function. We're just going to make a function here called log number, and it should take in what? Not the array, because we're thinking at the lower level, just one piece of data that we want to work with. Takes in a number, and it logs out the number. So we can test that real quick. And actually, this one doesn't really care if it's a number or a string. It's still going to work because we're just logging out a piece of data. And now I'm saying for each piece of data in my list of numbers, I want to log that thing out. How can I do that? Besides for loop. So for each dot nums. Yeah, so we want to use our array, and all arrays will have all these methods inside of them, so to speak. And you've used some of these before, like pop and push, right? And we also see map, which we'll get to in a second. But the one that we're looking for is this one over here, for each. And what we want to do, what does for each take in? And there's a little helper up there on the screen. It takes in a function. And so semantically, we talk about functions that we pass around, and we expect them to get called by someone else, in this case, the for each function itself. We refer to that as a callback. I'm saying, I'm going to give you this function. I want you to call it back for each number inside of nums. I want you to call it with the number and what else? So signature is up here. It's saying that for each takes in a function that they call the callback function. And that function could take in these three arguments. What are they? Yeah, so it'll take in the current value, it'll take in that value's current index, and it can also take in the array, which 99% of the time we don't care about because we already have it. It's nums. So what we're going to do is, how do I give for each this log number recipe? So not console.log, because in this case I only want to log out this one thing. And console log is going to log out everything that it takes in. So instead we wrote a function that takes one argument and logs it out. Yeah, so in here, in this space here, we can pass in a function. So I can define a function right here. But to simplify this, I define the function up here, takes in one thing, it logs it out. How do I give this to for each? Yeah, is this a variable? Yeah. It is. What's the variable here? Log number. Yeah, by defining a function in this way, I basically also made a variable called log number that's going to refer to this recipe of code. And so in here, how do I pass that function in? Yeah, I just give it the variable. That variable log number is actually a reference to how to do this. So all I'm saying now is for each number, give the current value, the current index, and the array to log number. And log number says, hey, I don't care about that second and third argument. I'm just going to take in that first one. I'm going to call it num, and then I'm going to log it out. And so under the hood, for each is going to do a for loop over all of the numbers. It's going to pluck out the current number, and then it's going to call whatever function I gave it with the current number. And we don't have to do that loop ourselves. So really, the only real line of code that we wrote here is basically line 10. When I said, think about our problem, what is the real meat of our problem? What do we want to do? Well, we want to take a number and we want to log it out. So all I did is wrap that in a function. That way I could reuse it over and over again. And now, because I know how for each works, I don't really have to think about this line of code. The only thing unique to my app is really line 10. So when we run that, we get this functionality right out of the box, and we didn't have to loop ourselves or care about indexes. So how could I modify this to also log out the index of that number? Yeah, so log number now needs to take in a second argument. And we know that for each will always pass a second argument, so we can call that index. And then just to use it, we could say that number is at index. And when we run this, we get all of that as well. Are you still with me? Okay, so I did get some questions this weekend. And if you wrote code or you write code like this, it's okay. I'm not making fun of you, but someone else in the class probably has the same question. And so I saw something like this. Is this valid code? Is this valid code? Line 17. Yeah. So the thing I'm trying to illustrate here is there's a huge difference between passing values to a function and when we define a function to take in a value. So when we define a function, this signature here, we're just defining variables that should take in a value based on the position of those variables when a function is called. We can't do any expression or any evaluation or any code up here. This is just the definition of arguments. So sure, when we go to for each, this value will really be a current index of an array, but I can't set a function up like that. So up here, I could say, hey, this function takes in two things, and the first thing, we're calling it num. I don't know where it came from. So over here, when I actually call log number, I could tell it, hey, that number you're going to use, it should really be the 0th thing of this list. But I can't, in the signature, say, hey, plug this thing into this other thing. Like, that's not actual code. So there's a huge difference between setting up parameters and then invoking functions with arguments that we want to evaluate. And so if this is something that you're struggling with, we need to take a step back and we really need to understand how functions work, how to use them, and how to define them. Otherwise, we can't get anything out of the rest of this lecture and yesterday, because these concepts are expecting that you know the basics of functions. And that's okay if you struggle with that right now. And if you know that this is a problem for you, then we need to review it until using functions is natural. And then we can return to this material. So do we have any questions on how to define and use functions? Because that's super important today. Cool. So anyway, we see here in REPL that it actually is just saying, hey, this red squiggly is saying, hey, I don't think that's valid code. Because you can't have brackets here. Brackets is like an evaluation of something. And we're not evaluating anything. We're just saying make an argument called num, or make a parameter called num, and its value should be whatever the first thing is that you pass in. That's really all the logic that we can do when we define functions. All right, so I said that for each is kind of our most basic, dumbest higher order function. It doesn't really give us more functionality other than going over every single number and calling a function for that number. But most of the time, we have a more specific use case of what we're trying to do when we loop over a whole list of data. And so one of those more specific use cases is map. Now, I've shown it a few times. Can anybody tell me in English what map does?
I think it runs a function on each index of an array and then replaces the result.
So you have the general idea, but the key word that I would say to avoid is replace. Map is an immutable function, so it's not going to edit anything on our original array. Instead, basically what map does is we say we're going to give it a function, and we're going to give it a list. So pretend we have 1, 2, 3. It's going to give back a completely brand new reference and if we pass it a function to double a number, basically it's going to take in the number 1 and say, hey, when I passed it to your function gave me back 2. So when I give you a new array, in the place of where 1 was, I'm going to give you 2. And in the place of 2, I'm going to give you 4. And in the place of 3, I'm going to give you 6. But it's going to spit back this array, and this array is a totally different reference. It's not actually going to modify the original at all. So if we want to emulate this right here, what is the meat of our problem? What do we actually want done? Okay, so let's write a function to double a number. What do I do? And how do we think we use this? What's that? Okay, so what's the thing that I want to operate on? Yeah, so I've got this one up here, right? How do I refer to it? Well, yeah, I've got that list somewhere in memory. What's my only way to access this right now? Nums. Nums is a variable that points to that array. So we want to do something with nums. And when I access this thing, we get a list of all of the methods that are available on arrays. So the one I'm looking for is .map. And .map signature looks exactly the same as for each. It takes a callback, and it will call back with those 3 values that we've spoken about a few times. Except the difference is that the map method calls the callback function 1 time for each element in the array, and then returns an array that contains the results of calling that function. So how do I tell map I want you to double all of those numbers? Yeah, I need to pass in a reference to this function here. And so why am I not doing this? Yeah, so it's like order of operations, right? We've got these outer parentheses for map. And before it can go to the map function, it needs to solve whatever expression is in here. So if double number is invoked, first, it's actually going to call double number with no argument. And what does that do? So it's going to be, x is undefined, but then if we take undefined and multiply it by 2, it's going to do something really wonky. And that's probably not the thing that we want to give to map. Instead, we want to give map just this function. So to do that, I don't invoke it. I just pass it in. Now today we're going to talk about functions that return functions. So if double number returned a function, maybe then I would actually invoke it right here. So we can't just make a hard-coded rule where it's like, hey, never invoke the thing that you give to map. But we have to be aware that if we invoke this thing, we get back some value, and that's not what I want. If it returned a function, maybe then I do want to invoke it. But so all these concepts build on top of each other. We have to understand what invoking a function does. We get a return value. And then in our specific use case, we have to know if that return value is a function, maybe that's what we want. But if it's not, maybe I just want to refer to it. So when we run this, we see that our original nums array is still exactly the same. It's got those numbers 1 through 7. But what map returned us was a new array that had the results of taking the 1, multiplying it by 2, taking the 2, passing it to double num, which basically multiplied it by 2, etc. And then at the end, if I check whether the new one is the same as the old one, we see that it's not. Why? Why is this false on 27? Yeah, it's a new reference. It's a brand new array. They have nothing to do with each other at this point. And so if we wanted to define this as an anonymous function, basically if I never want to use double number again, that could look something like this. All three of these examples on 25, 25, and 28, I'm passing a function to double nums. In the first case, I defined it up here and I had a variable. So we already built that function, we had a variable for it. On 25, I'm just inlining this value. Basically, this thing here is a function. It's only going to exist on that one line, but the order of operations with these parentheses says, hey, go figure out what the thing in the middle is first. Oh, it's just this recipe for a function. Let me give you that. And then on 28, it's the same thing as 25, except this is the cute little arrow syntax that basically says, hey, we can get rid of the function keyword. We can just take in arguments like this, and then the arrow signifies that it's a function. This basically says, take this argument, and if I'm only doing one line of code, I can omit the curly braces, omit the return keyword, and it'll automatically return this. So this says take something called x and return x times 2, which is the same thing we're doing here, and here, and here. Yeah.
If we want to do another operation here
On 28,
on the third one, how we will add it?
so if I need to do 2 lines of code inside the arrow function, I have to put the curly braces back in. So let's just say for whatever reason I want to double a number and then convert it to a string. So I just showed them that I have to do this on 2 separate lines. Okay, now I don't really have to do that on 2 separate lines because I could have just done this. But in the case that I can't just chain them all together, I need to do 2 different things. If I need to do multiple statements in an arrow function, I still use the curlies and the return keyword. I basically just get to leave off this function keyword and instead replace it with the arrow. That's not really important for today, but you're going to see arrow functions out in the wild because that's modern JavaScript, and it's easier to read once you get used to it. So if the arrow is throwing you off, don't worry about it. Write the anonymous function like this, or define it somewhere else and write it like this. The point is that all 3 of these are valid ways to pass a brand new function to map. Yeah.
So like if you, how do you write it if you define it again? If it's already defined, then you just call it by the function name and then and omit the curly bracket part.
So up here I have 2 ways to define a function and keep a variable that is a reference to it. So in both of these cases, my way to pass this function, my way to pass these functions are by their name. So in this case, I just give it the name. Because that name basically resolves to this, which is the same as if I did it without a name and I just put a function right here. In your head, you can kind of think that, oh, triple number, it looks up, it grabs this, and it basically copies and pastes it there. That's not how it works, but you can imagine it as the same thing. This is just one extra step where the computer has to look up what triple number is. And in this case, we immediately give it a function. Yeah?
But in 26, right, in line 26, technically numbers map triple number. Technically that this thing itself is not stored in a new variable.
The result of mapping the numbers? Yeah. So just to be short, yeah, this is a function. It's going to run, and right here on this line, it's going to be an array.
Right.
I didn't capture it 'cause I'm not doing anything with it. I'm just demoing how to use map. But that's correct. Yeah, we can run all sorts of functions everywhere and never capture them, and there's probably no point of our program. But just to test, sure, I could do that. So I'm just showing you how to use map, but here, yeah, it's pointless because I don't have a way to get the results of what tripling those numbers are, unless I save it.
Okay, so you could just assign it let trip num equals to num dot map that array.
Yeah, so if I want to capture this thing to use it later,
Okay.
nothing really changes here. This still all happens first, and then that output is what's giving to tripled nums. Map isn't functioning any different here. It's just before I wasn't doing anything with the result. And I'm saying save the result into this variable.
I see.
Yeah.
Are they all just was relatively different, or they have different efficiency?
Can you say it a little louder?
I mean, are they were ranked different, or they have different efficiency too?
So you're wondering if the different ways to define these
I mean,
have any differences kind of under the hood?
yeah, how they? I mean, what difference between them, like when we thinking about big O?
Okay, so as far as big O goes, any operation in JavaScript is constant. It just costs one operation to do it.
Okay,
So-
they are the same.
So they are the same conceptually. You know, if we really want to go under the hood, and for whatever reason we need to salvage every single nanosecond that we can, and every single bit that we save into the computer, then in this case, double number is going to take up space in the RAM of the computer when we save this into memory, because we're saving this onto the scope. But in this case down here, when I go to map, right after map runs, we don't have a way to use this ever again, which means that internally what happens?
Garbage.
It gets garbage collected. So this one's not going to take up any space in the computer. This one's still going to sit there even if I only used it once. So that doesn't matter. Like, that's never going to matter unless you're really fighting to be the fastest possible thing you could ever be and not save extra bits in the computer. But we're talking about a few extra ones and zeros being saved in memory to store this. It doesn't matter. Conceptually under the hood, that's cool to know what's actually happening, but that doesn't matter.
Yeah, actually,
Basically ever.
more thinking about the time, like which one.
Yeah, so when we evaluate how long it takes something to run, we always want to know worst case scenario, and it's always relative to the data that we're giving it. We don't really care how fast it works with just like one argument or whatever.
Yeah, sure. I mean,
So here, if we wanted to evaluate the runtime of how long does it take to loop over numbers relative, what do we think the runtime is here? How much more work do I do as my data set gets bigger? Like, what's the only relative thing to how long it's going to take to map over these numbers? Yeah, the size of the numbers, right? So I don't really care about the function because that's just going to happen once. Saving into memory doesn't matter at all. But in this case, as numbers gets bigger, so if we go from 10 to 100 numbers, how many operations are we doing under the hood? 100 or 10, right? So if we formularized that, it's really what? It's relative to how many numbers we have. So
ON.
exactly. And so in this case, if we're evaluating the performance of a program, I don't care about how this function was stored. I care how is it going to be relative to my data set. So O of n is pretty good. But if it was n squared, which means when we had 10, we do 100 operations. But when we have 100, we're going to do, what, 10,000 operations or 1,000 operations? So that relative difference there matters way more than the literally nanosecond to store that function. So we just don't
Yeah.
evaluate that at all. That's constant.
Yes. It means that we can
Yeah, I wouldn't worry about style and how you store the methods
Just
at all.
style.
We care about the algorithm, how it works compared to the data set, and how big your data set gets. Everything else I have here is a style preference. So sure, when you join a professional team, they may prefer to use arrow functions. But how we measure that on runtime doesn't matter. It's a great question though. Okay, so then one more. We've got one called filter.
Sorry,
Yeah.
so how is map different than for each again?
Does for each return a value? It doesn't. So for each is really stupid. It just runs your function. There's no result that we can get back. There's nothing we really do with it. We can do it if we're having like side effects, but generally we have a more applied use case on why we want to loop over stuff. Map is a really common one. We want to take some data and we want to map it. Like pretend I've got lists of names that users typed in. And I want to make sure all of them are now like punctuated or they have a space between the first and the last name. Then I'm going to map it through something that'll like sanitize that input. So I care about transforming it from like raw user input into like clean text. For each can't really help me there. Yeah.
In the previous example, if you call the for each method instead of the map with the same function passed in, it will mutate the original array.
It will not, because the function that I'm giving it is just taking in a number and returning the number times 3, right? But inside of for each, it doesn't do anything with the result of your callback. So yeah, it's going to still calculate what's 1 times 2, and then it moves on. It doesn't do anything with it. Map says, okay, 1 times 2, that function you gave me 2, so let me make a new array and start it with a 2. For each just ignores it completely. It's just like, hey, I ran them all. So it did calculate all these numbers, but it didn't do anything with it. Yeah.
Also, with the previous example, like when you invoke the how do you invoke the new function again?
How do I invoke what?
Say triple numbers.
So if I want to triple a number, I can call it myself. And what the fuck is this? Where'd that happen? If I want to invoke it, I just pass in a number. It gives me back that number times 3. Or yeah. But I'm not invoking it myself. I'm letting map do that work for me. So I never invoked triple number myself. I just wrote a way to triple a number, and I gave it to map. And inside of map's implementation, they'll invoke it for me.
Oh, so the same way you can pass in the array, and then the whole thing is going to run and map out the new array.
Can you refine the question?
Yeah. So right now you have triple number, right? If instead of invoking with the number 100, if you invoke it with an array, like the number array above,
Okay.
it's going to return a new array with each element of that array triple.
So why, if I give it to map, but yeah, if I'm just invoking triple number myself, let's think about it. If I pass in an array here, so I'm giving triple number an array. This is all triple number does. It takes in some values that it knows as y. It's going to take whatever that thing is and multiply it by 3. What does multiplying an array by 3 do? I have no clue because we probably never want to do that. Apparently this is what happens.
I actually meant triple numbers. Triple numbers is the variable that you store
The result of mapping the numbers times 3. So triple numbers is what data type?
so it's just an array.
Yeah, I get back something like this, except if I tripled them. Map takes the original, multiplies each by 3, and gives me a new array. And so I capture that. Triple numbers is basically what happens if we took every number in numbers and multiplied them by 3. Or in this one up here too.
Okay.
So I could go give triple numbers, I could go map over it and triple them again if I want. Good?
Yeah.
All right, filter. So what filter does is, in this case, we give it a function, and this doesn't really specify it, so let's go to the docs. So with filter, we give it a function that's known as a test function. And what they mean by that is the function we give it should return true or false. And it's going to give us back an array of all the elements for which our test function returned true. So over here, we've got this list of words. And the function that they give it does what? Exactly. So it's going to give us back a list of which words up here. Yeah, like I guess from exuberant on, right? Those are the only words in that array that are greater than 6. So at that point, like this, when the filter output has nothing to do with the original positions, they'll just be in order of the elements that passed that test case. So it says down here, in this case, the callback function is a predicate. That's another word for like a test function. It should return true to keep the element in our new array, or it should return false if we don't care about that element anymore. So what I'm saying now is if we had those nums, instead of having 1, 2, 3, 4, 5, 6, 7, I want only the numbers that are even. So what's the meat of my problem? What do I care about for each number? Yeah, so I have to write a function that returns whether one number is divisible by 2 or not. What can we do? So yeah, let's get used to the arrow. Let's set up a function that takes in an argument. The other thing about arrow functions is if we only take in one argument, we don't need to put parentheses around it. So we're going to take in one thing, and because we're looping over numbers, that number, I'm just going to call it num. And we want to return a true or false value, and that value should be whether num. Yeah, because the triple equals is going to force it to be what? True or false. Like I want to give back a Boolean. So if I do the triple equals against 0, it's only going to be true or false. So what's the difference between triple and double equals?
I know it checks also for type 2.
Yeah, so triples checks for type also. But double is still going to give me a true or false, right? It's just going to try to do some weird coercion first. And in this case, if I know for sure I'm taking in numbers, it's safe for me to do a mathematical operation like the remainder. So if I know I'm going to have a number here, and I know I'm going to have a number here, do I need triple equals? No, I could do double equals here. So like that's the thing, like you'll read that a lot of people will just scare off completely from ever using double equals. There's nothing wrong with double equals, but mentally we have to know, I don't care about type coercion because I'm using this when it should only be numbers. Therefore, there's no difference between 2 or 3, and that's your own personal preference.
Is
So-
it okay if I will use all time?
Yeah, especially if you don't want to have the headspace to think about it, you can use triple equals. Yeah. So we ran, let me comment off the old stuff, or we'll leave this. We took this list of numbers and we said filter it down to those that pass this function that determines if a number is even or not. And we got back a new array that has only the even numbers. Is the original numbers changed? No. So this is kind of a lot of functionality. Think about it. If you didn't know what filter was, what's the implementation here? Yeah, so first we want to return a new array, right? So you're going to have a function, you're going to make a new array, you're going to return the new array at the bottom. Then what's in the middle there? We got to do a for loop. We got to look at every number. Then we got to check if that number, basically this line of code here. If it is, if that number passes, what do we do with it? We push it into the array we're going to return. And so that's a bunch more code, right? We don't care about that stuff. It's generic. We're going to loop over it. We're going to run this callback. We don't want to code that all out. So we could just call the filter method and really only care about what was unique to our problem. And here, we just got to figure out if a number is even or not. Does that make sense? So that's a review from last week. These are just more useful functions. And map and filter, when you go to start practicing problems, is going to make life way faster than making that for loop yourself, especially if your function needed to multiply all numbers by 3 and check if they're even. You'd have a lot more code than doing it this way in basically 2 lines. So, in one go, I want to take my original numbers, I want to triple them, and I want to know which ones are even after the fact. How can I do this in one go? Okay, so we want to triple the numbers. So we're saying take those numbers and transform them by what?
By function.
Yeah, we already wrote this function, right? I think it's called triple number, yeah. And nums.map returns what?
Array.
Yeah, so this whole thing here is going to be an array, which means I can immediately do this. And now here's where we have a design question. Do I have an is-even function?
No.
But I have that logic, right? And I'm doing this logic in 2 different places. So it kind of makes sense that I would do what?
Function.
Yeah, let's take this recipe out and let's make it its own function. How do I replace this now?
Just write these.
Is even.
And so we see that when we filtered it to just the evens, we had this. But then when we tripled these things, and then filtered them by the evens, we ended up with this, which is 2 times 3 is 6, 4 times 3 is 12, 6 times 3 is 18. And then those were still the even ones. So 7 times 3 is 21. That happened in our map, but 21 is not even, so I don't see it here. So isn't this one line of code so much better than doing it yourself? It really is, because the only real lines of code that we wrote is how do we determine if a number is even, and how do we triple a number. Okay, so what if I wanted to instead quadruple numbers? What do I have to do?
Write the number.
Oh, so we have to come and say, and what do I do here? What do I have to change to get quadruple odd numbers?
Well, you said
What's that?
triple number.
And any ideas on what we can do here? I now want odd numbers. So I want not is even, right? But I can't just do this. because I'm passing a single value to filter, right? So the order of operations here is saying, oh, is even, that's a function. And the main operator is saying, take that function, get its truthiness, and flip it. So what am I actually passing to filter in that case? I'm passing in false, which isn't a function. So instead, I have to give filter a new function, right? What could I do?
We need to write another function. No?
So we could. What's the implementation of is odd? Yeah, but then I'm duping up this code here, right? Why reinvent the wheel and make a second place that I can make a bug? Something's odd if it's not even, right? So instead, I should reuse code whenever I can because it makes life way easier to maintain. So let's just use is even and flip that. And now if I wasn't going to use is odd in many different places, I only want to do it right here. Do we have any ideas on what I can plug in? Yeah, so let's take in a number and let's return the opposite of if the number is even. So this here is the same thing as this. But to get you more used to, this is what your code will look like in the wild if you're working with modern, competent developers. And this will get easier to read, but I want you to get used to it. Do we understand line 70?
This was a little bit confusing that is all what's happening when we do this, like line 66?
So it's order of operations, right? Over here, we're going to start, the first term we have to evaluate is because bang is kind of like a function. It needs a value to work with. And is even with this call isn't a value yet. So it says first, let's take that number and let's go to the is even function. And if the number is 10, is even returns what? True. So then we plug in that true here, and now the main operator says, okay, I got a single primitive value. Let me flip it. And so it'll take the true and it'll return false. So is odd for 10 will return false. And now all I did over here is I got cute because I didn't know if I'm going to use is odd over and over. So instead, this is how we can slightly modify a function. We could just pass in a real quick function that just flips is even. So that's one modern practice that you'll see. But where I'm getting at is what if your boss now comes to you and says, wait, we didn't want triple numbers, we didn't want quadruple numbers, we wanted numbers multiplied by 10. Are we going to come in here and make another function and hard code in this 4 and this 3? If we look at this, you can start to see a pattern, right? The only thing that changes is the number that we're multiplying by. So instead, there's maybe a way that we could generate a function that can multiply two numbers. And then I don't have to come in here and change code all of the time. I can let the user decide what they want to multiply by and immediately map by two numbers. And so that's where we're going today. And with that, these are now gone because I can generate them on the fly as I need them. So I haven't explained how this works yet. Take a second to just look at it and think about what is the return value of generate multiplier. So does this inner function get invoked anywhere? Cool, so this is a concept called closure that I'm going to walk through on the whiteboard how this works. But this one is a little bit more confusing, so we're going to come back to this. Let's take a step back instead. And quick review, why do I have an error here on line 24? So if we scroll back up, why is this an error now? Because triple number, before it was a function declaration, so it got hoisted. But now triple number is this assignment, right? It's an expression. So this doesn't happen until line 76. So I can't call it anymore all the way up here. So all of this is broken up here. So we're just going to comment that all off, but all of this will be in REPL. What? And another problem. All right, so this is the only thing we're concerned with right now. We'll come back to everything before. So let's just clean this up to look more familiar to you. What is going on here? All right, so let's take it slow and go over how closure works under the hood now. So on line 79, we're defining a function called makeCounter, right? So on my global scope, we make something called makeCounter. And when we did pass by reference, pass by value, I told you it works this way for functions, although I didn't really draw it out here. So when we make a complex data type, like an object, an array, or a function, what actually is going to happen on the board? Yeah, so we're actually going to go over here. And this is where the makeCounter function actually lives. It lives in memory. So that's kind of review. This is the state of our global scope. Okay, now, when we call makeCounter on line 88, I'm saying I want something called myCounter. I don't know what it is yet. To figure out what it is, we need to call that makeCounter. So we look up makeCounter variable. We find it's this memory address, and this is where that code kind of lives for that to run. And now when we call it, we make a functional scope, right? That's review of scope and reference so far. Now what happens here is as soon as we step into make counter, what do I define? Yeah, it makes a variable called count. And it sets it at 0. Then when we say return function, this is the same thing as when I returned like brackets and I made an array. Or I returned objects. Like I made curly braces and I returned an object, right? So what am I going to do next on the board? Yeah, we need to make some space in memory for this function that I'm creating right now and I'm going to return. So we come over here to the next memory address. So under the hood, functions are actually stored as objects. They have like a name property. And they're also going to hold something else that we're going to talk about in a second. But I didn't give you that visual for the original, but for this next one, it's important. So what happens here is we hit that return function. And when we define a new function, functions actually kind of take a little package that remembers the scope that they were defined in and what variables were there. So you can imagine that when we come to clean this thing up, it says, hey, we just made this function and it was inside of this scope. So it sees all of this forever. And it actually will always see the global scope. But to make it simpler, it says, okay, what's in my functional scope before I clean this up? Where it stored that function, it's going to have a list of the data that was around it when it was created. So in this case, we see, oh, we've got something called count. So where I live, where this function actually lives in memory, it's going to store an object that can access this count variable. So this scope kind of gets like packaged up and brought over to the function. So a neat little package of all the data it has access to. And now it's safe for us to clean up this functional scope over here. But it still lives where that function lives. And now because we're returning this, what did make counter actually return? Did it return count? It returned the function, right? What did we just create? We created this reference, right? So that my counter variable is actually a pointer to where we just created this function. So this thing lives on because we still have a reference to it now out on the global scope. So now later, I saved that thing as my counter. And when we log out the type of it, we say, hey, what is my counter? Oh, it's this memory address. So let's follow it. And this whole thing over here is a visualization of that function with its name and with its scope package. And so when we log out the type of this big thing over here is function. And because it's a function, it means that I can invoke it. So now when we invoke it, it remembers what this recipe is here. And the first line of code says, hey, do I have something called count on my scope? And it actually sees that it has a count on its closure, that package of scope that was made when it got created. And it comes over here and it says, let's increment that count to 1. And now we can log out, you've called me count times. And that was all that it did. It also returned the count just if I wanted it. But now when I call it again, it says, let's follow that reference. Let's go to that code. And it says, hey, do I have something called count? And I do. I find it in my closure. And it makes it 2. So in this way, we've generated a function. And that function is really the only way to ever modify that count. It's stuck in its closure, and there's no other code that can ever change this. It has its own count that it increases internally. So, That's review. I mean, it's not review from before, but what I just put up here is review of what we just did on the whiteboard. After we call line 92, my counter will have scope. It'll have a closure of count that will be at what? 2. Now when I call make counter again, what happens? I make a brand new function. I'm going to go do the same exact thing over here. I'm going to store all of the same thing. Except when we make that functional scope, it makes its own count, and it makes that count 0. So this thing and so now when I call other counter, what will we see come out on the screen? Exactly. These are two totally different functions that we generated out of here. They both have their own count, and they both know how to access their own data. So this is kind of similar to the phone book example. Remember when we made a function that spit out that object that could do phone book stuff? Like it was its own phone book every time we called make phone book. That's the same thing here. Every time we call this function, that makes a brand new function. The only thing we've added on today is that functions can remember what their kind of nearest scopes were, and they'll have access to it forever. But there's no way in code out here that I can ever modify count without calling that function. It's like encapsulated in that scope. There's no way I can access it and say, hey, go to my counter and just completely change count. I can't. So this demo that I have right here, how this is useful in real life, is this is if we wanted to do something that's called like make a spy. Basically, we could instead, and I might be jumping ahead of myself, but instead we could like give make counter its own like function. And it's going to return a function that will actually call our function. But it has this additional functionality where it can keep track of how many times you call it. So sometimes in testing, we'll have a function that we're going to use, and then we'll pass it through something like this, where basically it will always increment the count, and then we'll call the function that you wanted. And then we can know how many times a function got called. So that's called a spy. That's basically what we've done here. We're spying on how many times this thing gets called. So last demo is, let's just say, yeah.
If you had set other counter equal to my counter instead of make counter, would you have run into the issue where it like looks to the same spot in memory pool and just starts at 3?
Yeah, so if I said let other counter equal my counter, so I'm not calling make counter. It's kind of the same as with arrays and objects, right? So instead, on line 91, when this happens, what do I fill in here? Yeah, I say, what is my counter? Oh, it's this memory address. So you should be the same memory address. So if I log out if they're triple equals, they're the same thing. It's the same reference. I didn't make any new function. I didn't make any new closure. So now when I call other counter on 100, what will I see? 3. That's a good question. That's exactly how it works. It's like the reference stuff is no different than the objects and arrays. The only thing we've added today is that functions actually remember their scope. So I made one more change here. What did I do? What variable did I add? Global counter. And now when I call these functions, they look and they say, let me go through my scope lists. When I look for count, I check my own closure, and I find it. When I look for global count, I do check my own closure. It's the same as when we had that functional scope over here. But if I don't find it here, or I didn't find it in the closure, we go find it on the global scope, right? So now, after I run other counter, how many times will we expect to see this? What will the value be? Why did I break? So we made this counter function. When we called it the first time, it says, hey, I've got my own count, let's make it 1. And then I don't find my own global counter, so I go to the global scope, which I defined up here, and I increment that to 1. And I log out, hey, the global is 1. And then I call the same my counter again. It says, you've called me 2 times, and I increment the global. Now I make a brand new make counter, and it says, you've called me 1 time. I don't have anything called global counter, so I look all the way back to the global scope. That thing got modified by the other one to be 2, so I'm now making it 3. So in this way, they can still access the global scope, but they also have their own closures. And the only variable in here that's in its closure is what? Count.
If you log global counter,
Yeah.
right? Okay. So the global the counter, which is let global counter is assigned to 0. That's being incremented, correct? So this is a good example from the lecture, like the call stack, right? Like the logs and then goes up.
So I wouldn't mention the call stack much here because it's still kind of flat. It's kind of like while we're out on the global scope, or the global call stack, the main thing that we're doing, we're just going to process make counter. And make counter is pretty quick. It doesn't call any other functions. It just returns this one. Then we're back out at like a flat stack. So it's more so it's a visualization of the like looking up the scope lists all the time until we check our inner scope. If we don't find it, we check the next scope until we get to the global scope. So call stack will work similarly to that, but we're not there yet. That's tomorrow. So tomorrow we'll take a little step back. I think that recursion might actually be a little bit easier than this. This technique of closures isn't understood that well, so it's okay to be freaked out right now. But if you can grasp the counter examples here, that's pretty much the whole idea. If you can have this visual of, hey, they store a scope with that function, that it can access its own scope forever, that's really important, and that's super powerful feature in JavaScript, which we're about to demonstrate where it's more useful. So this is pretty much a practical example, but we'll come back to that. Okay, and so today is hard, I know. And we've kind of gone already as deep as the slides are going to go, but I think to really help you understand it, it helps to see how are these things actually used in real life. So I have a few more examples in the REPL, and then we'll rip through the slides. But do we have any questions so far? Cool. So with this in mind, maybe I shouldn't have filled this in yet ahead of time. So we kind of see where I'm going with this one. So the only difference between these two, does this returned function, does it have a closure? Think about it for a second before you shake your head. It looks a little bit differently, but when we run generate multiplier, does it put anything on its scope?
Yes.
What does it put?
The argument when you call
Num to multiply by, right? So that's no different than what happens here on line 84, where we made a count. It's just in this case, we make it as soon as you call the function based on the argument. So in this case, when we call generate multiplier with 3, it's going to make a functional scope over here and say num to multiply by, I know this is ugly, is 3. That's same as when we made count equal to 0. It's just initialized by this instead of hard-coded down here. So now, when it creates this thing, it is going to go make a reference, and it is going to put num to multiply by on its closure. And so it's going to spit back a function that takes in one more argument every time. It's going to take in a num. But num to multiply by has basically been hard-coded to be 3 at this point from example 76. Like, I have no way to ever go and change that after I initially call it. So what is the type of triple number? It's a function, yeah. Generate multiplier just returns a function. But that function will actually remember, hey, I came from the time that you made num to multiply by as 3. And quadruple numbers, it's like, hey, I remember the time that you called me with 4. So if I call triple number with 7 in here, it says, okay, num, you just gave me a 7. Do I have a num to multiply by? I do. It's on my scope, and it was initialized to 3. And quadruple number, num to multiply by, is basically hard-coded to be 4. Still with me? Do you see where that's getting useful?
You have to create another variable to get num.
Do I have to actually get a multiply here?
No, to get num. Instead of you said some triple number equals
So functions, this isn't useful at all. But to show you, the function, the stringified version of this function is literally the code here. I mean, it's not going to replace the variable, and I can't actually see its closure. But both of these functions do the same thing. They look like this. The only difference is that each of them looks somewhere else for what num to multiply by is. And so now these, triple number and quadruple number, they work exactly the same way that they worked before.
I forgot about
Yeah. So now if we go back, do I still have nums? Yes. Now, your boss came to you and they said, I want to multiply every number by 60. What can we do? Yeah. I need a function that takes in a number and multiplies it by 60. Yeah, so I have a function now that can give me a function that will multiply numbers by 60. So what I want to pass to map, is it that? No, because what is this?
Taking the value.
So right now, just this variable, what is it? It's a function, but this isn't the function that I want to be mapped over. Instead, I really want this, right? It's the return value. How do I get that? Whoops. And so now this is where all of our knowledge comes together to say, what is actually being passed to map? An order of operations means it's the result of calling this thing. And calling this thing gives us back a function. And that one takes in one thing and multiplies it. That's what we want to give to map. And that's what I was saying before. We can't just hard code in our heads, just give a name of the function. Because in this case, we actually want to invoke this first to get back a function, and that's the one we give to map. Does that make sense? Cool, so now when we log out the result, we have all those numbers multiplied by 60. And so the real benefit of this is that, well, we still kind of hard-coded something in here, right? We hard-coded the 60 in our code. So our boss told us we want to multiply by 60. We still had to change something here, even though it was less code to change. But the reason this closure thing is super useful is because I can make this completely dynamic now, right? So you don't have to know this function, but out. So this function here, prompt, it's used on websites to put up a text box and take some input from a user. And now because REPL is actually running on their server, it didn't work. I had to put it in the Chrome console. But regardless, if this code was on a website, this is what would happen. And so I can give them a number, and it's over here. So over here we see that I gave them 1,000. So let me just fix everything in here to run correctly. And then what do I want to do? Instead of hard code the 60 here, what do I really want? Yeah, I want to put the number I just got from the user. So let's just fix this. Get out of here. Now what am I plugging in here? I've got a way that it'll get a number from a user. Except when that text box pops up, what type of data do we think it is when I type and hit enter? It's a string, right? And if I multiply by a string, we're going to have problems. So what do I need to do? So yeah, whatever I get here, I need to make it a number, right? So do we see all of the concepts from this course, how they come together like that? We really have to think about what each individual value is. Once we start plugging these things together, life gets easier. So really, I'm just going to wrap it in the number constructor. It'll convert that string to a number. And now we can take this, and I have to reload the whole page so the Chrome console clears itself. But we can come in here. We could just paste all of that. This is no different than how it is in REPL. I just have to do it here. And when that happens, it says, give me a number. What number do we want? 1,000. We could do any fucking number we want, and it'll multiply all of them now. And look at that. We hard-coded nothing. If you were on a project that needed this type of functionality, and you don't know how to use Clojure, you can't get this done in this way. And that's why there's going to be a huge skill differential between somebody that can do this and someone that can't. And that's why my code base on my team has so many functions hard-coded over and over and over again, and all it leads to is problems. It's a lot more code to try to handle every possible user choice that they would want than if we could just generate the recipes that we need. And this will always work. So that really shows you the power of this and where it's useful, because the slides kind of just show you how this works. But I think we actually kind of get scope. I mean, Clojure, even if we wouldn't know how to make it useful, if we can understand this concept here, we're in a really good spot. Now this concept here is really hard at first to grasp. This is not required to finish the rest of the course or to get into the boot camp. So you can come back to it when you have time, and you find that you have a bunch of functions that have some pattern. Like we saw, the key to do this was because we wrote two functions that take in one number and multiply it by a hard-coded number. So the thought process was, how do we get rid of that hard-coded number? And the answer was to do what? Make a function that returns a function, and instead of that hard-coded number, it's the argument of the first function in a Clojure. And now we can use it to multiply by whatever we want. Okay, I'll do these tomorrow. This is another really great real-life example. But basically imagine it's called caching, which means, hey, we might have some function that, let's say we wanted to sum up every number from 1 to whatever number you gave it. Well, the first time we do it, you give us the number 500. We have to loop from 1 to 500, and we have to return that total sum, right? But if you give me 550, and this was a nice code base, do I have to start from number 1? I've kind of already done most of the work to sum up from 1 to 500. So instead, I can write something like this, where I can store all of the results I've ever calculated. And if you give me 550, I can go say, oh, the biggest one that I've done so far is up to 500. So why don't I start with the sum that I returned when I did 500, and now just go from 501 to 550. Does that make sense? We're not going to do the code right now. But just wrapping the function that'll do that summing with some way to cache a previous result can be a huge benefit in your code base. Imagine if we had a site that does this for millions of users. And millions of users all the time are asking, hey, sum up everything to 1,000,000. And someone over here says, sum up everything to 1,000,000. The answer doesn't change, but it's going to take time for that for loop to do 1,000,000 iterations. So why don't I just do it once? And now the second guy that says, hey, I want to sum up to 1,000,000, let me just give him the result of the last time. That's going to have a huge performance impact on your server rather than starting from the beginning every time. So with that in mind, because there actually is going to be a question today that asks you to do this caching system, what data structure do we think we could maybe store previous arguments and their results? An object. Yeah, we're going to have a function that spits out a function that actually does the looping. But first, we can have something called a cache. And we could say, if the argument you just gave me, if that's in my cache, let me just return that. If it's not in my cache, we'll actually do all of the work you just said. And so the one we give you today will be simpler. It's going to be make a function that first makes an object, then it returns a function that will do the work you want. But in there, it'll also say, if the argument you gave me is in my cache, let me return it. And if it wasn't there, and I just had to calculate it, before I finish my function, I'm going to store the result you just, I'm going to store the argument you gave me and the result I just calculated. So I'm not going to do that right now because I see that you're overwhelmed. We'll review that tomorrow, but that is on the workshop today. And so nothing really changes, except in that case, in our closure, we're also going to store a cache. And that's a real useful example. That's very high level and impressive if you get to that when you're actually on the job search. Someone doesn't know, it's the technique here is called memoization. Basically like remember the arguments and make a way that you can reuse old arguments to get old values. But it's not important to get into boot camp, but it's super cool. Yeah. Yes, similar. I mean, there you're going to have a lot more complexity in terms of how it works. But yeah, in machine learning, that's how the computers get smarter, right? It uses ideas that it's already figured out once to now do harder and harder work. And then a neural network gets even more complex than that, but similar idea. And that's how they learn.
Similar idea, like we are creating objects and we are storing in object all this
Yeah.
stuff.
Objects are super useful, and it's more than just giving a person a name. And it's because of that ability, I said when we use objects in this way to store a unique value to a unique key to a value, what way are we using objects as? What did I call it? What's that? They are complex, but I said when we use an object this way, it's called a hash. So in the phone book example, we hashed phone numbers to names. And in the cache example, we're going to hash arguments to values of what happens when we ran a function for that argument. All right, so last thing, and this also I think gets used in workshop today, so it's not a waste of your time. I want to make a times table. So I want to have functions that I can multiply by 1, 2, 3, 4, 5, 6, 7, 8, 9, etc. I've got a list of numbers here. Do we have any ideas? How can I generate all of my times table functions? Times table is like 2 times 1, 2 times 2, 2 times 3. So we're not at that point yet. But to do that, I need a function that multiplies things by 2, right? So I need functions that multiply by 1, 2, 3, 4, 5, 6, 7, 8, 9. What can I do?
Would you do something similar where you did, where you have a function and then you're incrementing the value of it?
Yeah. So I do have this function that I can use to generate my multipliers. But then I also have a list of numbers that can be used as what?
As the number would be used to multiply.
So how can I take, thank you, yes. So let's take all of the numbers that we have here. And what am I going to do?
What is the function? And pass the value.
And nums.
So what do we think? What do I actually want this time?
Pass the argument.
You need to iterate through.
Put the arrays in the
So I don't need to do any of that because map is going to say, let me take this 1. Let me pass it to generate multiplier. Generate multiplier returns what? A function. So yeah, I'll get an array where in this position I have a function. That's what I want. So actually, to make this easier to use, let me do a 0 there. What do I expect to see inside of this array? Exactly. And in the 0th spot, the version of the function that I got back here will have a closure where num to multiply by is what? 0. So now I could do stuff like this. Or let's pick a different one. So think about it for a second, the order of operations here. What is multiply func? So the multiply func itself is an array of functions, right? So if I access the second index, what is that? That's now a function. And we know that function came by taking this number and passing it to generate multiplier. So that function now, because it's a function, I can invoke it with the parentheses, right? So we solve this, we solve that, and we're saying invoke that thing with 3. So now it actually runs this. And num to multiply by is what? And num is, so we will get and again, the real only application level logic that I've coded here is what? Yeah, generate multiplier, sure, that's true. But the real logic, the only logic that's relevant is here. So if instead now I wanted to divide, I change one thing of code. Or I can expand this to be able to give me multiply, add, subtract, divide. And then I can even make a function that will generate times tables, addition tables, subtraction tables, division tables. That's how it all builds up on top of itself. And that's why functional programming can make you what's called like a 10xer, which means you do 10 times the amount of work as 10 individual junior developers. Because you're going to code stuff like this. That's all generating lots of recipes with not too much code. Sure, it's a lot of headspace right now, But that code base would be way cleaner than the junior that typed out all of that. And you got it done in a fraction of the time. That's where the skill is. And a lot more money. But you'll still make really good money as soon as you graduate regardless. So there are probably other ways that we can make nested tables and make this resemble a times table with an easier interface than this. But we see that this isn't too much code for a lot of functionality, right? But yeah, I just made that a little bit more complex. The only thing we really care about is this little scope. It's just a little package of taking that functional scope and just saving it with that function reference. All right, how do we feel? Are we mad at me? A little bit? Cool, to the slides. And now you're going to crush these slides, I think. Where are they? Do you want a little break? Anybody want a break? Okay, take a 2-minute break. That was a lot.
Any like good links
For
for the basically what you just showed us over the end.
So there's definitely a good link that I'll send out about map filter. And the last one that's really important, have you seen it anywhere?
I think that's
No, I'm wondering if you know the name of the function I'm referring to. Reduce.
reduce.
Yeah, have we seen reduce anywhere? So it's probably like that's like your holy grail of beginning higher order functions. And so map and filter, they're kind of similar. The callback takes a current value and an index, etc. Reduce is basically if instead of mapping over a list and giving me a new list of all the values, what if I just wanted one value? So like reduce all of those numbers and sum them all up. And so with reduce, basically it takes two arguments. It takes like your current reducer and it takes the current value. So imagine that basically we give reduce, we tell it start with the number 0. In the callback, the reducer value will first be 0. And then the thing that was at the 0th index, let's say that it's 1. We're going to return the reducer value plus the current. So we return 0 plus 1. Now it goes to the next number. And it says, hey, the current aggregate value is 1. And your number is 2. And you return aggregate plus 2. So now it has 3. And then it goes to the next one. So reduce is the last higher order function I didn't want to bother you with yet, but it's also super useful for beginner programming. It's like map, filter, reduce. If you can learn those, that's really good for problem solving, and you'll come back to this. I didn't start using this till I was at the boot camp on campus here.
Which one was the one you said you got wrong and then you learned during the interview?
Recursion. So we'll go over that one tomorrow.
Okay. Hey, you.
Yeah.
It is, right?
So this was my talk when I was a senior here. And basically, this is taking that pattern idea of, hey, all times that we query a database can actually be made into patterns. Like you don't know any of this code, you will. But basically it's like, hey, go to like the table on the database that I want with the type of query I want to do, like find one, find all, find by ID, with the arguments that I want to give to that query, and then with whatever I want to do afterwards. And so this is a function that takes in one argument, that returns a function that takes in one argument, that returns a function that takes in one argument 5 times. And with this one function, I can generate every single query that you'll ever do in your application. And I never have to do this in many places. And so this is actually really, really powerful, but obviously a much more advanced level of what we're doing right now. But with the idea of closures, and then when you learn how to actually talk to a database, this would be really flexible and maintainable in your back end. Like I can generate every query that you'd possibly want just by knowing the different tables in your database. And so that's what my talk was on. Oh, we just cracked 5,000 views, so I'm excited about that. But yeah, I didn't know what the fuck I'm talking about because I'm still a junior developer at this point, right? So iBase was like, I think this is a good idea. I don't know if it actually is, but because people have commented and has a bunch of views, I guess it is useful, so I'm proud about that. But at Bloomberg, we don't use code that's advanced enough for me to do this. So I really want to go to a modern place where I can write code like this. Because instead, my team writes queries in strings, and we plug values into strings, and it is a mess. And there's thousands of them when we could do it with one function. Anyway, you'll get to all that. Is everyone back? Then there was one more thing that just reminded me of, and I forgot it. Oh well. All right, closure. In your own words, what is closure? Someone tell me. Sophie.
It's a little packet of information that's taken from the local scope of the function.
Yeah, it's just a package of scope. And functions will always remember the scopes that they were defined in. Whatever variables it had access to when it was created, it will always have access to it when you invoke it. Even though it looked kind of weird, right? Like it looks really weird, and that's what's tricky about this. This is not the REPL. Like one tricky thing here is like, we're invoking this counter out on the global scope. So in our heads, we're like, it's no longer like in here. So how does it like use this count? We're not inside of here anymore, right? Isn't that kind of confusing? So the answer is that they always remember and have access to the scopes in which they were defined, regardless of where you actually invoke it from. Now that's tough to wrap our heads around, but that definition of closure is exactly how it works. Cool, so this only occurs when we return functions from functions, because that means we're creating a new spot in memory to refer to that function. That's also where we store other stuff, like its name and its scopes, although you're never going to be able to see that programmatically. So we know that functions can return values. Do we feel good about this slide? Yeah, pat yourself on the back. You've learned something. You've come this far. You have learned something. Even if I throw it all out the window and this scares you, you have come a long way. So be proud about that. And in the previous unit, we learned that functions are like any other value, which means what? As far as last class, what did that mean? What was our new thing that we did? We can pass them into functions, and today it means that we can also return functions. So in this case, we're returning a function. Where does greet_me live? What scope? It lives on the global. And getGreeter, for whatever reason, says, hey, return greet_me. Does it find a greet_me inside of here? No, but it does find it on global. So this isn't really practical, but getGreeter will give us a reference to this. So that means the type of greeter function and greeter triple equals greet_me is what? Does it say yes? What does it tell you? Triple equals says what? Yeah, so it says, what's the value we get back? True, yeah. That's what you mean by yes, true. And when we invoke greeter, it logs out hi. From what line? What line logs out hi? 2, yeah, greeter is the same as greet me. And in this case, are we returning a reference to greet me? What are we returning? We're not returning that. So what happens here when we invoke greet me? We run this code here. Is there a return keyword? So we return, yeah, don't get tripped up on the console log. It does absolutely nothing. And so when we call getGreeter, this returns the result of what? The result of calling greetMe, which returns undefined. So getGreeter returns undefined. So type of greeter and console log greeter. And what happens now? Yeah, we just said that greeter is going to be undefined. Can we put 2 parentheses next to an undefined value? No, so JavaScript freaks out. Good, it's a good thing it does. So now coming in a little bit closer to REPL, getGreeter, what does it put on its scope? Yeah, function call greetMe. And then it returns what? Does it? And so what is greetMe? It's a reference to this function that we define right here. Make sense? We define basically a variable called greetMe. GreetMe is a function. Then down here we return that function. Does greetMe have a closure?
No, it's console log.
Okay, so technically, greetMe does have a closure of the scope inside of here, but there's nothing defined there. We're not using it yet, but it does remember this scope it was defined in. There's just nothing there. So calling getGreeter gives us back what type of thing? A function, which means I could do this. And now, what do I see on the screen? There we go. So we can return anonymous functions too. When we call getGreeter, what do we get back now? Yeah, this is no different than last slide. We said return this thing. This thing means we have to go create a complex data type, which is a function, which means we will make a reference to it. It does have a closure, but there's nothing in the closure, but we get that back. So when we call getGreeter, we get back a reference to the version of this function that just got created. And we can invoke it to see hi. Now I say let greeter2 equal getGreeter. Does greeter2 equal triple equal greeter? No. Why? Yeah, every time we call getGreeter, it makes a brand new function. So triple equals no. What about double equals?
Maybe.
Why maybe?
Maybe they can have the same value.
Nope.
No?
So one, yeah, they're not the same. They're not the same. With complex data types, it's brand new, got created differently, brand new reference.
For functions,
Double and triple equals really aren't going to have different effects on complex data types. Definitely not the same. But I think you're messing with me.
for functions, it's like double and triple the same for functions.
Yeah, they're going to have the same result with complex data types because both of them just say, hey, are these the same reference? When it's complex, it's not really going to coerce the complex data type because how could you? All right, what about if our return function takes a parameter? This doesn't really change anything up. It just means, hey, when we call getGreeter, we get back a function that expects to take one argument. So when we call greeter with Marie, Marie is the value of name, and we log out, hi, Marie. Still haven't got crazy yet, right? And on line 12, why do we get high undefined? Because we didn't pass in an argument, but this one says, I don't care if you pass one in, I'm always going to use this thing. You don't give me anything, so its value is basically blank, which is undefined. So it still logs out high undefined. Before we talk about closure, which you guys are now experts in and you love it, let's review how scope works with nested functions. So that's basically referring to this. When I said like, hey, if we were two functions deep, we always look at ourselves. Then we look at the function above us until we hit the global scope, right? That's review from scope day. So inner functions can access variables defined in outer functions and in their outer functions all the way until you hit the global scope, right? So when we call greeter and it makes a name called Marie, it makes its function here, and then immediately calls that function, this one says, do I have anything called name?
No.
No, this one does not have, it looks at its own scope first, here, in these brackets. It doesn't have a name. So it looks one level up in these brackets and sees that name is Marie, and it uses that one. If there was a name out on the global scope, would we see it?
No.
But if I commented this off, would we see the global scope?
Yes.
Yeah, and if I had a name inside of here, doesn't matter if there are other names, we won't see those either. 'Cause it starts looking here, then looks outward. And closure, that's it. That's how scope works. The only thing with closure is that it can still do that even when we call it later on. But the scope works exactly the same way. Even if you want to totally forget that I said it's like a little package. It still is looking in the same spots. It's just that they'll have memory over like when they were invoked, which is their count variable. Like 2 of the counters we got out of there have completely different counts. That's like the added addition of closure. But the way the scope lookup works, it walks up the tree the same way. So closure is the fact that an inner function can still access values defined in the outer function even after the outer function is finished running. And that's what I demoed just now in REPL. I said, doesn't it look weird? Like we're calling it out here, but it was over there. That's what they mean by after it's still running. So get greeter. When we call this, it'll log out, hey, get greeter is running. Then it makes something called name is Marie, or name variable and has Marie. And I say get greeter is finishing. When get greeter finishes, it creates a brand new function and it returns that function. So when I first call get greeter, do I see this happen? No. So on line 13, what do I see go on the log? Are you sure? So this says run get greeter. Get greeter is running. It does this thing. It logs out that it's finishing. And then it returns a function. It doesn't do this console log at all. So when it returns a function, that means that greeter is what? Yeah, it's a reference to that function we just created. So if it's a function, that means that I can invoke it, right? Now when I invoke it, what do I see on the screen?
Hi.
Hi, Marie. Yeah. So it says, hey, run that code in here. And this one says, okay, I'm running this line. Do I have a name inside of this? No, but it does remember this is the scope I was made in. Let me check there. And it will find this name Marie. Even though it's out here on the global scope, it still remembers it came from there. So the last most complicated thing is that instead of hard coding name to be Marie, we can get that in the closure, in the scope, when we first call get greeter. And this is the step that we did when we made make multiplier. So now instead of hard coding it to be name Marie, we can get a function that will always greet the name that we created when we first called get greeter. So in this case, get greeter runs, it would say get greeter is running. But name has been set to what? Because that's what we passed in as the name when we first ran getGreeter. And when this function gets returned, it does remember the name, that whatever name was when it got created. So when we call greeter on line 9, it will say, hi, Rosalind. Which means if I wanted a way to greet Marie, what do I have to do? Okay, so not change it. I want to greet Rosalind and Marie. What do I have to do? I have to call, yeah? No, say. What do you mean by second argument? Oh, okay, you took me literally when I said I wanted to greet both. That would work, but I want to greet them separately. Yeah, so here I've got a function that will always greet Rosalind. I'm saying I also want a way to greet Marie. I'd have to say, let greet Marie equal getGreeter and pass in Marie. And then greet Marie will basically always remember, hey, the name when I got created was Marie. And this one, the name when I got created was Rosalind, because that's what will be in their closures. But, yeah, the reverse is if I wanted to be able to greet two people, well, we could take in name and we could take in name too. And I think the next slide covers this. But what if I want to, when I first create it, I want to greet one person. But the next time you call it, I want to also add in a second person. What changes now? How do I take in that second person? Where do I create the variable? Over here. So if I want the second time you actually invoke this thing, I want to say hi name and by name 2. I can put the name 2 here. And to use that, I can put that here. We'll have the visual on the next slide, I believe.
That's an example of saying if your boss tells you to, now you want to say bye to, so you do. Right?
Yeah, basically by putting it here means, hey, whenever I invoke this returned one, we can always change it. But the one up here basically is like locked in place. That's how we made the times table. We said, hey, the number to multiply by, whenever you call the return function, this one's stuck to whatever it was when you first called it. So we pass in 2, we got back a function that will always multiply by 2. But what it multiplies to the 2 comes in when you actually use it for real over here. But we'll see that. Here we go. What if both functions take parameters? This is putting it all together. It doesn't get harder than this. At least conceptually. Once you have the concepts, that's when you can build that crazy shit I just showed you. But the concept doesn't get harder. In this example, what is name 2? Rosalind. And name 1 will be Marie. So I've got a function, basically greeter, will always say hi to Marie, and then whatever you call it when you actually call the inner function will be the person that you're introducing them to. Does that click? Good, this is it. This is today's entire lecture. And this is just a little bit simpler than the multiply numbers, but the concept is exactly the same. And then, because we understood that concept, we threw them in arrays and accessed them differently. But still, the closure is the same. Questions on this slide? Okay, and this is why I said it's really important that we have to get the differences between setting up function parameters and setting up arguments. Marie and Rosalind are the values of arguments here, and the parameters are always known as name 1 and name 2. And so with that, we can now make as many functions as we want that will always say hi Marie or hi Rosalind, and then wait basically for the next time that you call it with the person you want to introduce Marie to or introduce Rosalind to. Does that make sense? That's it. Any questions? Okay, and then one more thing, but this one is kind of simple. I just want to show you one other way that this could be useful. So this is how I think console log should actually work. All I'm doing here is I have a function that takes in an argument and it's going to log it out, but it gives back a reference to itself. Any ideas on why I would do that? Or how I might use this thing? Come on. It's not. It's a similar idea, but it's not recursion. And maybe I can't demo it the way I want without going more complicated. Or this is a little broken. But anyway, when you call console log with multiple arguments, it kind of strings them all in one long line, right? And sometimes that's hard to see. Sometimes I would prefer log out the first thing on its own line and then log out the second one and then log out the third. And so if calling console log returned itself, then we could just keep putting parentheses on the end of it. Yeah, here we go. So we see here, basically when I call log with line 1, it's going to log out line 1 on its own line. So that's the only thing I gave console log. But because it returns log, that means that this first bit here resolves to the log function. So I could just invoke it again and again. And just as a difference of why I think this is annoying with console log, so sometimes I don't want all these things in one line, but I also don't want to type console log 3 times in a row. So it would be easier if I could just close parenthesis, open parenthesis, close parenthesis, open parenthesis. So that's all I did with this, my custom log function. It's just another way that we could use functions, returning functions, to do other stuff. And here there's no closure or anything crazy, but to me this would be easier than to having this, or if I actually wanted, if I wanted the same functionality, this is what I have to do. So I think console log should just return itself. But it's too late for them to ever fix that because it will break everybody's code that might have something just like sitting over here. Anyway, that's it. Just another way that returning functions could be useful. It just means that we could chain them forever like this. All right, final questions. Cool. So today is probably the hardest one after pass by reference versus pass by value. And then tomorrow is probably the third hardest one with recursion. But it's okay if we don't feel too great about this. It's just you'll come back to it when you have the headspace. But tomorrow we will need to know for admissions interview. But I think it'll be a little bit easier than all of this conceptually. Maybe. I don't know. We'll see. This is the hardest 2 days of the course. So don't beat yourselves up. You have infinite time to come back. And maybe it takes actually writing out like a bunch of those patterns before you have the drive to say, okay, I think I'm ready to eliminate this redundancy and make functions that generate functions. Does not require. So more so, focus on map, filter for each. That's really going to help you in the short term. And this stuff we'll come back to. Just work through the workshop today, and then you could discard it if you'd like. But use the help tickets, message me privately if there's anything you want to talk about. And I'll open workshops, send out pairs. Cool? Cool, thanks for being good sports. That was hard.